And also thank you for giving me the opportunity to present our work in your seminar. Yeah, so this is joint work with Florian Maire, who is also a professor at Université de Montréal. And yeah, so you said the title, so lifted samplers for partially ordered discrete state spaces. So it may look fancy at first, but don't worry if you don't know a lot about lifted samplers or partially ordered spaces. I will go through this in detail during the talk. Okay. So I will now describe the structure of the talk. So I will start with a simple example and then a real example. Okay, so the simple example will help me to set the scene for the next part. Okay, so you notice probably that you have basically the same sections in both parts. It's just that it will be easier to explain in the more complicated setting of partially ordered spaces, because in the first part, it will be the case, it will be a totally ordered space. So I will describe the context. I will recall what is the Metropolis-Hastings algorithm, MH algorithm. Probably you already know this, but anyway, I will just go through this. And but going through this will help me to define the lifted version, and I will present a remarkable theoretical result that is not from us, actually. It's from Christophe Andrieux and his co-author. And I will continue with the second part. And the second part is more like our contribution. Okay, so in this simple example, I will consider principal component regression. Okay, so the whole talk I will consider the context of variable selection. Okay, so it's just like, it will be like this the whole talk. You will have only one thing to remember: variable selection. Okay, so here you have principal component regression. We are like in a Bayesian statistics setting. And so imagine, so principal component regression is just like where the regressors are principal components. And so imagine that you already decided, you have fixed like a maximum number of principal components that you want to include in your model. But now, using like the linear regression and the dependent variable, you want to choose like how many components are actually useful in the modeling. Okay. So we have access to posterior model probabilities up to a normalizing constant. So we are able to integrate out the parameters. So this happens, for instance, when the errors of the regression are normals and you have conjugate priors. So basically, we have this PMF, okay, and we are interested by it because it will help us to decide like how many components we should include in our final model, in a sense. So in this case, I will define by X the model indicator. So this thing, basically, for X fixed, it tells you like which model you are looking at. Okay. So in this case, X is a totally ordered set. Okay, because this model indicator can take values in the set 0, 1, 2, okay, until P. And what we mean by, those numbers is just like, for instance, when X is equal to 0, it means that you have 0 principal component included in your model. If X is equal to 1, you have 1 principal component, and it's the first one, okay? When X is equal to 2, you have 2, and it's the first and the second one. So when you specify that X is equal to a number, for instance, K, that you have the K first principal components in your model, okay? And this is like, in some sense, to be consistent with the principle of principal components analysis. Okay, so this set is totally ordered because you can take two models, so model 1 and model 2, and you know exactly that they are comparable. So 1 is smaller than 2 in the sense that model 2 has 2 principal components and model 1 has 1 principal component, and you're able to compare every pair of model like this. Okay, so this is what we mean by totally ordered. So this is like not a realistic setting, okay, because you would imagine that even if P is, in some sense large, I don't know, 100, 1000, you have access to the PMF, so you can compute your things like as usual. But I want to present MCMC, so I will just consider that we want to sample from this target distribution pi, which is the PMF of the models. Okay. So we want to do this. So how can we do this? We know that a solution is a Metropolis algorithm. So we'll go through this quickly because you're familiar with that. Let's say you are at a current state X. In this case, we will use like a symmetric random walk proposal. So you go to x plus 1, you propose x plus 1 or x minus 1, probability 1/2 each. You accept this proposal, meaning that you will, the next state of the chain will be y with this probability. Otherwise, you remain at the same state. You loop over these steps. So this acceptance probability makes the Markov chain pi reversible. Okay, you know probably this condition. It's a local condition that ensures that the detailed balance condition is satisfied. Okay, so in this case, we know that pi is an invariant distribution. With this kind of proposal, we know that the chain is irreducible, so you can reach any other state in a finite number of iterations. And usually, because you have an acceptance probability, you have a positive probability of staying at the same state for 2 consecutive iterations, meaning that the Markov chain is aperiodic. So everything is all right, your chain is ergodic. And if you compute ergodic averages, you have approximations of expectations under the target. So for instance, if you count the number of ones in your sample and you divide by the number of iterations, it gives you an approximation to pi of 1. Okay. So let's say you implement it and so you get this, okay, in this example where it's just a representation of the PMF, okay? So, so the horizontal bars basically tells you the probability of a state under the target. Okay, so you have something unimodal. So the longer the bar, the higher the probability. And you use a random walk proposal, so you have a random walk behavior, so a lot of oscillations. And so basically you see that going from 9 to state 9 to state 2, you make it, but you have a lot of back and forth. And basically this is not good. There is a rule of thumb that says that if you use a random walk like this, traversing a distance of d will take roughly d squared iterations. And like exploring the state space slowly is something that is not good for MCMC. And it is reflected in the ESS, which is 0.9 per iteration in this case. ESS stands for effective sample size. And in this case, it would mean that if you have a sample of size 11 of your Markov chain, this would give the same information as 1 IID draw, okay? So what do we want to do? We want to still sample from pi, but we want to avoid this random walk behavior. Okay. We'll apply the technique of called lifting. Okay, so it's something that was introduced quite a while ago, as you can see, but it is only recently that we realized that it could be actually useful in practice. Okay. So why this technique is called lifting? It's called lifting because you lift the state space in the sense that you extend the state space to add something, okay? In our case, we will add the set -1 + 1, okay? So if we add a set to the state space, we want to associate to it a variable. And in this case, the variable, what it does is that it's a direction variable, okay? That will be denoted new, that has a uniform distribution over this set, okay? And what this direction variable will do is that it will basically guide the Markov chain to have persistent movement, okay? It will help us to not have this random walk behavior, okay? So the target is now, instead of being just pi, is pi times this uniform. But there's no problem with this because, as you know, you can still just compute ergodic averages by looking at the first component of your Markov chain, forget about the direction, and you will have still approximations to like marginal expectations, okay? So the algorithm is similar to the MH, Metropolis-Hastings, but now we have like two components, x and nu. And the difference is that instead of like choosing between x + 1 or x - 1, given a direction, we choose with probability 1, we go to x plus nu, okay? We accept the proposal with the same probability as before, okay? But when we accept, so we go as before to y, but we need to decide what we do with this direction, and we keep it the same. So basically, we continue going in the same direction as long as we reject. When we reject, we stay at the same state x, but we flip the direction. Okay, so if you remember the target that we had before was some kind of unimodal, okay? So you can imagine that if you are like in the tail and you reject, it's probably because you have no mass beyond, you know, the state x in the direction that you were going. So you flip the direction and basically you are going back to the area where the mass is. Okay, so it seems, all this seems intuitive. Okay, and so we have again this like local condition, but in this case the chain is no longer reversible. Okay, this local condition is similar to like what we need to have detailed balance, but because we have a direction, we doesn't have detailed balance. It's something similar that is called skewed detailed balance. Okay, and now the chain is non-reversible. So basically, this direction nu, what it does, in a sense, is that it helps us keeping track of the past. Okay, so while retaining the Markov property. So we don't know where we came from, but we know the direction that we were using. Okay, and that will help us in the sampling. Okay, here is what we get on the same target as before, and so we see the difference in ESS. And for instance, you know, we go through the state even to 10 in this case, and when we go for instance from 10 to 2, here the PMF is strictly increasing. So we know for sure with this lifted sampler that we will make it in one go. Okay, there will be no backtracking because we will accept, you know, step after step, and we will keep going in the same direction. Okay, so it's something interesting, something really good. Okay, so it seems like it does well, but can we have like theoretical guarantees? And actually, we have something. So Andrieux and Livingstone, 2019, there was like a paper coming, a preprint coming out on Archive, and the result that I will present you is a corollary of theorem 2.17 in their paper, in their preprint. And what they do basically is that for the first time they were able to, we have a way of comparing non-reversible Markov chains or non-reversible samplers with reversible samplers. Okay, the thing that we were able to do before was comparing reversible with reversible. And the way they do this is basically, I told you that we have something that is similar to detail balance, that is called like skewed detail balance. And basically they kind of exploit this fact. So it's not reversible, but there is like a specific form of non-reversibility. And the result that we have is an order on the asymptotic variance. In this case, it's for the discrete setting and totally ordered state, okay, what I present to you. So we consider any function f of x, okay? We need to consider only functions of x because, you know, those like MH and the lifted sampler, they are not even defined on the same state space. So we need to deal with like the same objects. But when we just consider functions of f, we have an order on the asymptotic variance. I will not give like the detailed definition, but basically it tells you like when you have reached stationarity, and then you just look at the variance of the kind of the approximation that you will get, then this order tells you that one approximation is more accurate than the other. Okay? And what is really remarkable with this result, there are a couple of things, but the fact that we are able to obtain this for the lifted sampler it's good because it's good, but at the same time, it's not so surprising. It's good because the lifted sampler is implemented at no additional computational cost than MH. So this is something remarkable to have an order like this for no additional computational cost. And also this is true for any target F, okay? So this is quite special. And the other thing that I wanted to mention is that, yeah, it's not, you have to consider that it's not so surprising because basically you have the same acceptance probability, but you have the persistency, okay? So it's like these two things together, they ensure that the sampler is good, and that's basically what we see here, okay? And there's something else that I want to tell you on the theoretical side. So actually, the lifted sampler, we don't have directly that it dominates MH, okay? What it does is that, what we know is that it dominates another Markov kernel that is its reversible counterpart, okay? And I will define this sampler, okay? So it's defined also on the extended state space. And the difference is that instead of, you know, like keeping going in the same direction until you reject, basically at each step, you kind of refresh, as in HMC, you refresh the direction. So you kind of pick a new direction every time. So you still have that when you accept, you keep this new, but in fact, it doesn't change anything. And this new step makes the chain reversible. And also you can verify that basically you have the same transition probability as MH, okay? Because, you know, with probability 1/2, you pick -1 and then you propose X -1, okay? And you have the same. So it's just that in this case, this reversible counterpart, it corresponds to MH. Also, there is another like interesting thing to notice here is that you could see this reversible counterpart as being like another way of writing the MH algorithm. So you could say like, I will write this MH algorithm on an extended state space, even if it doesn't change anything. And the lifted sampler basically is just like forgetting to refresh the direction. Okay. Okay, so that's it for the simple example. I will go on with a real example this time. So so it's still variable selection, but here it will be just like no principal component things, just like normal variable selection. So I consider US crime data that were analyzed in the 70s by people in social sciences. And they use the linear regression, okay, of, so the dependent variable is the crime rate, and you have 15 covariates. And an example of covariate is the mean years of a given data created by state from 47 US states in 1960. So this means that you have 47 data points and you have 15 covariates. Okay, so you have this number of models. As this data set was analyzed several times in statistics, for instance, by Raftery and al. In 1997. So it's a paper that came out in JASA, and it's about model averaging in linear regression. Okay, and what we realized is that actually model averaging and lifted samplers, they have something in common. Okay, and I will explain to you what the point in common is. So basically, imagine that you want to do model averaging. So you have a couple of models, but the mass on the model, it concentrates on one model. Okay, so your model averaging doesn't give you much. Okay, it doesn't change anything from just using the model with the highest probability. Okay, and so it is really useful when the mass is kind of spread out over several models. And with lifted samplers, we want the same thing. Okay, because if the mass is concentrated on a few states, we will have no space for persistent movement. Okay, so you remember the previous example, we have like a couple of states that were like probable, and the chains were able, you know, to have like persistent movement. So in this case, X will not be written as a subset of the integers because there's no principal components as before. So we want to consider every model. So we write in this case X as a vector of P components. Okay, so as before, we have like integrate out the parameters, and we have access to the unnormalized posterior model probabilities. And the components, they can take the value 0 and 1. So for instance, if x1 takes the value 0, it means that the first covariate is not included. When it takes the value 1, it is included. Okay, so for like x fixed with like zeros and ones, you know exactly which model you are looking at. Okay, and we will see that this this set is not totally ordered. Okay, so to explain this, I will define the following order through the set R. So I have this pair of state, x and y, and they respect some conditions. So imagine that you fix y. So basically, you look at models that are nested in y. Okay. So when you have like such a pair of x and y, we say, and x is different than y, we say that x is smaller than y using this order, okay? And we will denote it like this, okay? So just to be like 100% clear about why this is partially ordered, I will give you two examples. So in the first one, you have this model, 1, 0, 0, 0. So only the first covariate is included. And y, you have 1, 1, 0, 0, 0. So the first and the second covariates are included. So x is nested in y. So it means that like these states are comparable, okay? Because I'm able, they belong to the set R, okay? So a second example, you can look again at this model X with 1, 0, 0, and this model Y. In this case, it's 0, 1, 0, 0, 0. So these models, they both have one covariate that is included in the model, but X is not nested in Y, and Y is not nested in X, okay? So in this order, they are not comparable, okay? So, so in this sense, it's not every pair of X and Y that can be ordered, okay? So that's why it's partially ordered, okay? Well, I think it's kind of clear. Okay, so the MH algorithm in this case, it's really as before, but I will highlight now that you need to define neighborhoods. Maybe it's not as trivial as before. And also, I will use this notation to introduce our methodology. So you have to implement the algorithm, you need neighborhoods for all x, and you need proposal distributions, qx, which support the neighborhood of x for all x, okay? As soon as you have these two ingredients, you're able to implement the algorithm, which is also the same as before, really, but just using this new structure. So here we have to include these probabilities because it's not like as before. And now you have, so again, a reversible sampler. So to be like completely clear about how you can choose the neighborhoods and the proposal distributions in our example of variable selection, I will present them. So you could set the neighborhood of x to be the models y that are such that you have this condition. So the sum of absolute differences between like the components is equal to 1. So it basically means that either in y you will have a 0 that will be flipped for a 1 or 1 that will be flipped for a 0. Okay, so you look at models that have one additional covariate or one less covariate. Okay, so you could you could choose like the proposal distributions in several ways, but like a traditional choice is the uniform. Okay, so the uniform over the neighborhood. So in this case, the acceptance probability would be given by this. And it simplifies actually to this in our case because of the kind of neighborhood that we use. So to see this, it's just because all neighborhoods have the same size. Okay, whatever x or y, whatever the state you are looking at, basically the models, you will, as I said, you will flip a 0 for a 1 or a 1 for a 0. But basically you have P choices, and this is what is chosen uniformly at random, because once you sample from like a number between 0 and 1 and P, then you know which component you will flip, okay? So that's why they all have the same size, and it reduces to this. So the acceptance probability is simple, but the sampler can be quite inefficient, okay? And that's what we notice, and I mean, a few people noticed that. So you could use something more sophisticated. For instance, there is this locally informed proposal distribution that was proposed by Zanella in 2020. So it's proposal distributions that are efficient in high-dimensional settings, and they are like this. Okay, so you have this function g of a ratio, and here you have the normalizing constant. And this function g is a positive continuous function that of this argument divided by g of like the inverse of the argument equal the argument, okay? And having such a property that is like, by the way, respected by the square root, just g could be the square root, you have that the acceptance probability reduces to this, okay? So a ratio of normalizing constant, okay? But having this doesn't tell you really that it's a good way of choosing your proposal. But the idea behind this method is that if you look at a state space that is like quite large compared to the size of the neighborhoods, okay, and in the limit, as this like difference gets larger, you would no longer need the accept reject step. So using such a function g leaves the distribution pi invariant. And in fact, Zanella proves in his paper that this ratio under like some conditions converges to 1 in the high dimensional setting, okay? So, so if I use the MH with the Zanella proposal on the example that I described, this is what you get, okay? So you still have the random walk behavior, so a lot of oscillations. But in this case, X is no longer like one-dimensional, right? So if I show you a trace plot, I have to decide which function or statistic I am looking at. And the statistic that I chose is the number of covariates included in the model, okay? And it makes sense to use this statistic because it tells you that if you move a lot with respect to this function, then it means that you explore the whole state space, okay? So again, we want to avoid this kind of random walk behavior, okay? So our contribution, one of our contributions is to basically propose like a generic recipe to come up with a lifted sampler when you realize that you have a partial order, okay? So imagine that you already have your Metropolis-Hastings algorithm, and so now I will give you the step to make it lifted, okay? So we start with like from the same neighborhoods, but now we need neighborhoods that depends on X and nu, okay, the direction, because we have a direction. And what we do is that we split the neighborhood X in 2, okay, and we use it using the partial order, okay? So basically, like, you know, when we were in like one dimension, it was easy to decide, like, you know, when you have a direction, which state is next, you know? But here it's not clear. So using this partial order, kind of X is multidimensional. It kind of reduces locally. You have a statistic in one dimension using the partial order, and we use this to kind of induce a direction and persistent movement. So when you follow the direction +1, you look at states y that are like greater in this partial order. So if we consider the variable selection example, we would take the neighborhoods that was formed from like models with one more covariate and one less. And when the direction is +1, you just take the models with one additional covariate. And when you have the direction -1, you just look at models with one less covariate. Okay, so you split it into like this, and you define like proposal distributions on now QX new that is restricted on this neighborhood n nu of x. Okay, so you know exactly which neighborhood you will look at, and you will follow a direction in this sense. Okay, so the algorithm is as before, and you have instance this acceptance. You have this acceptance probability that now depends on nu, and here is what we get, for instance, in this example. So we see that, you know, we have more like straight lines, and we see the difference in ESS. Okay. So we looked at this, and, you know, because the basic inspiration of this work was the paper by Andrieux and Livingstone. We saw their result, and we were like, okay, lifted samplers, they seem to be quite good. So first, can we do something beyond like totally ordered state spaces, and can we get like theoretical guarantees? Okay, so in this case of partially ordered, can we get something as strong as before? So I will recall that the lifted sampler, what we know, okay, is that it dominates its reversible counterpart. Okay, it's just that before the reversible counterpart was equal to MH. Okay, in this case, what is the reversible counterpart? So it's the lifted sampler with this added step of like direction refreshment. Okay, but the difference now is that it doesn't correspond to MH. Okay, because if we look at the acceptance probability, we have a ratio like this. Okay, and now like the size of the neighborhoods, they are not equal because they depend on nu and minus nu. So if you think of like, in this case, when I look at uniform distribution, okay, they are not equal, and I will show even more clearly on the next slide why, but they are not equal. Okay, so it doesn't correspond to MH. So you have like two things that kind of are in contradiction. You have the persistent movement, but on the other side, you have a difference in acceptance probabilities. And what we saw, I mean, is that it leads sometimes to like smaller acceptance rates, and so we cannot have something as strong as before. Okay, we cannot hope for something that is as strong as before, and we have examples in the paper where we see that the lifted sampler is less efficient than MH. Okay. Okay, so it's okay, a little bit sad, but can we have something? And so we wrote the acceptance probability like in a different way, and we saw that there was probably something. Okay, so I will define two things, n1 of x and n0 of x. and it's the number of ones that you have in your vector, and the n0 of x is the number of 0, which like the two objects are related because p minus n1 of x is equal to n0 of x. Okay. So if I look again at the acceptance probability, if I have the direction +1, so it's given by this when the proposal is uniform, and you can write it this way, okay? Because if for instance you consider this size of the neighborhood of x with direction +1, it's equal to n0 of x, okay? Because the number of models that you have with like where you have the possibilities of adding a covariate, it's the number of zeros that you have in your vector x, okay? And for the same reason, this thing, you can write it as n1 of y. N1 of y, you can write it as p minus n0 of y. But n0 of y is n0 of x minus 1, okay? Because if you are adding covariates, your model y will have one less zero than in x, okay? So if you look at this, then maybe you start noticing that there is a way of having something similar to MH, okay? If P is large and N0 is close to P divided by 2, then those things, they are similar, okay? So it means that, and it's true also for the probability of proposing a value y, okay? So it means that if you have a Markov chain, imagine that you have a Markov chain lifted, in this case, with the uniform proposal distribution, and the mass concentrates on these states, okay? That are such that, you know, you have n0 of x that is close to p divided by 2. Then you have a sampler that behaves like MH. So if the reversible counterpart behaves like MH, then you can hope that the lifted will be better. Okay? And that's basically what we proved. So it's an asymptotic scenario where, in this case, P goes to infinity. Okay? And so you define a sequence of sets X star subscript P. Okay, here in this slide I will have everything with a subscript P because you know, it depends, it's a sequence on P. So this state, this set is included in the state space, and it's formed of states such that n0 of x and n1 of x are close to P divided by 2. So imagine that the target concentrates on this set at some rate. Okay, we have the details in the paper. Then for any epsilon greater than 0 and for any sequence of functions f of p, you have this inequality. So you have an order on the asymptotic variance, but it's no longer like, it's not a guarantee as before. But you see that if epsilon is small, this thing is close to 1. This is the variance of f under pi. So if this is not too crazy, then if you multiply by something small, you get something small plus something small. So this inequality suggests that the lifted sampler is better. Okay, and this is for sufficiently large p that depends on pi and f. Okay, so in the paper we also have like a result like this, but using like the Zanella proposals. We also have like a way of using like the same technique, but in the trans-dimensional setting. So it could be used for any variable selection setting. Also, we have an example with the Ising model. Okay, and the way that we prove some results like this is kind of using kind of a more general inequality than Pescoun inequality, because Pescoun you need like an order on the Markov kernels for every pairs of x and y, and in this case we just have it on a subset, but the mass outside of the subset, you know, it vanishes, and we are able to get results like this. Okay, so just to tell you a little bit the ideas and what you can find in the paper. Maybe one thing that I can say before like closing the talk is that the version that we have on arXiv, we have a version of this work. It was like, so first submitted in March, and at the time it was quite preliminary. Now we feel that we understand more, and we will have a new version soon on arXiv. Okay, thank you, and maybe you have some questions. And I also have the references.